All right, so far this week we've talked about torque and we've talked about moment of inertia. In today's lesson, we're going to bring those two concepts together to get a more clear understanding of how rotational motion works. And the way we're going to do that is by talking about what we call Newton's second law of rotational motion. Uh, Before we go there, I want to review Newton's second law for linear motion, which you may remember is that the acceleration of an object equals the net force on that object divided by the mass of the object, or rearranged, that's our force equals mass times acceleration. But for today, we're going to focus on the iteration of this equation that is acceleration equals force divided by mass. Okay? So if we think about this, this is for linear motion, and what we're going to do to think about the second law for rotational motion is just replace these variables with variables that are more useful for rotational motion. So acceleration is pretty easy. That's going to be rotational or angular acceleration. Instead of force, remember that the force is only going to be as effective as the ability for the force to cause motion, and that effectiveness is measured in torque. So you could have a strong force, but if it's not applied correctly, then it's not going to do anything. So in this case, instead of force, we're going to use torque. And the mass, again, mass is only as important as where the mass is distributed. And in our last lesson, we learned about how different shapes have the mass distributed differently, and that impacts their moment of inertia. So that's what's going to be used in this in this equation. So our equation for Newton's second law of rotational motion is rotational acceleration equals torque divided by moment of inertia. Okay? So keeping this in mind, and keeping in mind how we find torque and how we find moment of inertia, so just as a quick review of that stuff, if you think about torque, remember torque equals the force times the radius, and depending on if there's an angle involved, then sine theta. Remember, if it's applied perpendicular, then that sine theta will equal 1, so it's just torque equals force times radius. But if it's not, the force is not applied perpendicular to the object, then it's important to include this sine theta. And then our equation for moment of inertia, at least for a hoop, is I equals mr squared, mass times the radius of the object squared. Okay? So we'll keep those in mind as we work through this practice problem. Our problem is, so a solid steel wheel has a mass of 15 kilograms and a diameter of 0.44 meters. It starts at rest. So if it starts at rest, that means it is not moving. The angular velocity is 0. You want to make it rotate at 8 revolutions per second in 15 seconds. What you want to find is what torque must be applied to the wheel, and if you apply the torque by wrapping a strap around the outside of the wheel, how much force should you exert on the strap. Okay? So first I'm going to draw this out. We have a solid steel wheel, okay? And the diameter is 0.44 meters. Okay? We want to get the angular velocity up to 8 revolutions per second in 15 seconds. So our final angular velocity is going to be 8 revolutions per second. But remember, we never want to actually use revolutions per second, and we're always going to be using radians. So we need to use a conversion factor to change this to radians. So rather than 8 revolutions per second, we need to think how many radians are in a revolution. So we have a conversion factor of 2 pi radians are in 1 revolution. Revolutions cancel out. We do 8 times 2 pi gives us, what does that give us? 3.4? No, hold on. That's the acceleration. Times, it was 8. So 50.24 radians per second. And we want to do that in 15 seconds. So now we're thinking, okay, our equation for angular acceleration, which is what we're looking for, would be the change in angular velocity over the change in time. If we start from 0, then our change would be that 50.24, and our time would be 15 seconds, because that's how long we want to take to get up to that speed. So 50.24 divided by 15 seconds. Now we have the 3.34 radians per second squared. Okay? So now we've found an angular acceleration, but really what we want is torque, how much torque needs to be applied. But because we've just learned about Newton's second law of rotational motion, that's pretty easy to find now that we have angular acceleration, because the angular acceleration equals the torque over the moment of inertia. Okay? If we need to find torque, that means the only thing that we need to do is find the moment of inertia, and we can do the torque will equal the angular acceleration times that moment of inertia. Okay? So I'm going to walk through how we find the moment of inertia. Again, we need to pull out important information. So it tells us the diameter, which will help us to find the radius, because we know that's always going to be involved with our moment of inertia equations. Our base equation being mass times radius squared, and then the potential to put some kind of fraction in here depending on the shape of the object. So we have the mass of the object, 15 kilograms. We have the radius of the object, or we have the diameter, so we can find the radius. And then the only thing we need to do is think about the shape of the object. So it says that it is a solid wheel. All right. So instead of a hoop like we worked with when we talked about moment of inertia before, now the weight is distributed across the wheel. So this is a solid cylinder would be the shape that we're working with. And the equation for that is I equals 1/2 mr squared. So if we do this equation, our mass is 15 kilograms, but because we're working with 1/2, we're going to do 15 times 0.5 times r squared r being half of the diameter, 0.44, so r equals 0.22, 0.22 squared. And so we get 0.36 kilogram meter squared as our moment of inertia. Plugging this back into the equation we talked about over here, the torque is going to equal the moment of, or the angular acceleration, which was 3.3 radians per second squared, times the moment of inertia, which was 0.36 kilograms per meter squared, or times meter squared, sorry. And so if we do that equation, we get 1.2, and the way that this works out with the, if we're using the kilograms and the second squared, we're going to end up with a unit of Newton meters, so N times M. So that's how much torque needs to be applied. And now we need to figure out how much force you exert on the strap. Okay? So if we're looking at how we want to do that, we are going to come back to our equation for torque. So torque equals force times radius. And then because we're applying it at a perpendicular angle, we're going to ignore the sine theta, because that will just equal 1. So we're just going to stick with torque equals force times the radius. The radius in this case was 0.22 meters. So we're going to rearrange our equation to have force by itself. Force equals torque divided by the radius. So the amount of force applied needs to be 1.2 Newton meters per 0.22 meters. Remember, this will cancel out. And we're left with 1.22 divided by 0.22 would be 5.5 newtons. Okay? So this is how you would walk through using all these different variables of rotational motion in one problem, going from step to step, looking at what pieces of information we have, where we need to get to, and what equations we can use to get there. Okay? And we'll talk more about this in person. Thanks.